All right, so what we want to do is we want to relate this quantity in this dimension to seconds here, this other dimension. So how many seconds are there in 50 minutes? So this is probably a calculation you can just figure out in your head, but the way we do this using dimensional analysis is we multiply this by a conversion factor, one or more conversion factors. And so the goal of the conversion factor is to convert from one dimension into another. So what we want to do is we want to convert from minutes into something else, you know. And so we need to be able to cancel out the minutes. So therefore I write the minutes in the denominator here, but I need to relate that to something else. And so what can we relate it to? The best thing to relate it to would be seconds. So if we were relating minutes to seconds, that would be the most direct way of doing it. And we can do that by saying that there are 60 seconds in every minute, or 60 seconds per minute. That's one way. And so this is called a conversion factor here. And we'll look at more of those later. And so here, the conversion factor is 60 seconds in 1 minute. The minutes cancel, that leaves us in seconds, and then we just do 50 times 60. 50 times 60 here. 50 times 60 would be 3,000 seconds. End up with 3,000 seconds here. Okay, the conversion factor, we'll talk a little bit more about conversion factors here in just a second, but conversion factor is just some equality. So, for example, here, this would be conversion factor. 0.025 furlongs is equal to 1 rod. I don't know what furlongs or rods are, but this would be an equivalency here. So whenever we're given a relationship like that, we're relating a dimension to another dimension here. We can use it in one of two ways here. And so this would read 0.025 furlong is equal to 1 rod. And so it depends on what we need to cancel out. So, for example, if we need to cancel out rods in the numerator, I'd write furlong in the numerator and then rods in the denominator. So rods can cancel out. Or if I need to cancel out furlongs, I could write it, just flip it over, 1 rod per 0.025 furlong. And so basically all three things say the same thing. 1025 furlongs per rod. That's it. And so the oldest horse racing track in the United States is 8 furlongs long, I think. What is the length of track in rods? So the start is, okay, we have 8 furlongs. Yes. And so what we need is we need something that can cancel out furlongs. So I'll put furlongs in the denominator here so I can cancel out the dimension. But I have to relate it to a new dimension here. So it looks like I can just relate it to rods here. 1 rod per 0.025 furlongs. And actually that's what I want. I want rods here. So how many rods is that? That's 8 divided by 0.025. Which comes out to 320 rods. So this is the gist of the dimensional analysis. These were all one conversion factor. Sometimes we have to use multiple conversion factors. But these conversion factors, we've got to get good at finding them. The conversion factors are just these equivalency expressions. These are like 2 or more things. And we can write it in 2 ways, depending on what we want in the denominator. So let's take a look at these here. That's dimensional analysis problems. Okay, 1 day is 24 hours. And so here, there are 2 ways of writing that. One way is put days on the top and hours on the bottom. The other is to put hours on the top and days on the bottom. So these say the same thing, and they do different things depending on what we want to cancel out. my car averages 17 miles per gallon. So I got 17 miles on the top, gallons on the bottom, or 1 gallon on the top and 17 miles on the bottom. So again, there's 2 conversion factors. Yeah. All right. These 2 conversion factors, there's one more thing about the numbers that we need to talk about, and that is exact versus inexact conversion factors. And so 1 day is, by definition, 24 hours. That means it's 24 hours is exactly 1 day, correct? Or is it about 24 hours? 1 day is about 24 hours, which means it's not really exact. You know, it's anywhere between 23 and 25 hours, what do you say? Or 1 day is 24 hours. 1 day is 24 hours. So this is what we call an exact conversion factor. However, my car averages 17 miles per gallon. Does that mean I'm going to go exactly 17 miles for every gallon? No. And so this would be an inexact conversion factor. And there's a difference here. Even though both of these are 2 digits long, we treat them differently. And so when something's exact, we say it has an infinite number of sig figs. Exact. And so 24 hours being exact, number, it is a little different than this one. This one is not exact. And so 17 miles has a different meaning here. And so when it's not exact, it depends on how many digits are written. This is written to 2 sig figs here, what we call significant figures, or SF. Significant figures. And so when something's not exact, then what we typically see is that there's going to be a range associated with it. So for example, 17 miles could mean anywhere from this. That means that the average miles per gallon might be anywhere from 16.5 to 17.4. And so this a range. This is like the uncertainty range here. You know, there's going to be some uncertainty associated with that average. You know, is it exactly 17 or about 17? Well, if it's about 17, then we expect 16.5 to 17.4. So, for example, sterling silver. Is sterling silver exactly 92% silver, or about 92% silver? It's about, so sterling silver is about. And so if sterling silver is about, that means it's anywhere from 91.5 to maybe 92.4% silver. Silver, do you know the symbol for silver? AG. AG. That's a symbol for silver. So if you go and buy sterling silver, it's not exactly 92. Most likely, I think most likely it's on the lower end, from most vendors. That way they save money. The rest is copper. Copper is a lot cheaper. But to qualify as sterling silver, it has to be 92%. Does it have to be exactly? No, it has to round to 92%, like this. Well, the same thing here, 16.5 rounds to 17, 17.4 rounds to 17. So this is the degree of uncertainty, because 17 miles per hour, or per gallon, could mean anything in this range. And so this is the range of uncertainty we have here. So what's the range of uncertainty in 24 hours? How much uncertainty do we have? Does 24 hours, does that mean anywhere from 23.5 to 24.4 hours constitutes a day? This is the range of uncertainty in the hours per day? No. And so when it's exact, it means that we have 24.000. We have an infinite number of zeros following this. And so it's right on. It's exact. We call this definition, by definition. So this is a definition. However, when we're looking at the average miles per gallon, That's not by definition. This is an inexact number. And therefore, these two numbers, this one has no uncertainty, it's exact. This one has some uncertainty, it's not exact. Just like sterling silver. Sterling silver has some uncertainty. If you have a piece of sterling silver, can you tell me exactly how much silver is in there? No, you can tell me approximately how much silver is in there, but not exactly, right? If you have 3 days, can you tell me exactly how many hours there are in 3 full days? Yeah, you can tell me, that. And so we're going to keep track of that because the numbers, they have meaning to them. We need to know that. And so what we've been doing so far is something called dimensional analysis, or this is the algorithm, quote unquote, in solving quantitative chemistry problems. First we analyze the problem statement. We determine the quantity and the units or the dimensions, what's given, what's desired. We look for conversion factors here. I wouldn't bother writing these rules down because you're going to get so much practice with this. You don't really need to write these down. This is not anything special, and you can deviate from this algorithm, it's no problem. And then construct a setup. And usually when I construct a setup, I don't know where I'm going. I rarely have things mapped out, especially if I'm doing things for the first time. But that's a good thing about this method, is you don't have to know exactly where you're going or what you're doing. And so what I do is I just start off with my given. I start off with 672 hours. And what they want is they want us to figure out how many weeks is that 672 hours. And so what I'll do is I'll just, I don't come up with like a mental map of how I'm going to get there. I'll just try different things. So one thing we'll try is 672 hours. We need to get rid of hours and go towards weeks. And so do you know how many hours there are in a week? Do you have that memorized? Well, we can figure it out, but I don't have it memorized. But I do have one thing memorized. I know that there are 60 minutes in 1 hour. Is that exact? Are there exactly 60 minutes in 1 hour? Yeah, that's exact. So we call that infinite sig figs, exact. There's no uncertainty there. Now, this uncertainty has to do with precision, Like, let's say you're going, let's say you're looking at this, 1 inch versus 1.0 inches. 1 inch, that might be exact, but it's ambiguous. Or it might be what we could say 1 sig fig. If it's exact, then we say there's infinite sig figs. It's exactly 1 inch. If it's 1 sig fig, then it's approximately 1 inch. Approximately 1 inch just means that there's going to be uncertainty how precise that is. So, for example, the uncertainty here could range from 0.5 to 1.4 inches. And so it could be anywhere from a ½ inch to 1.4 inches, but that would still qualify as 1 inch, right? It's like sterling silver. As long as it qualifies as 92% to 2 sig figs, you're okay. Then you can call it sterling silver. But if you start to cut it down, let's say you went from 91.5 to 91.3, then no, that's not sterling silver because it should be 92, right? But still, there's some what we call uncertainty there. That uncertainty is precision. Versus this, this one is not exact for sure. This is not exact. This one would be what we say is 2 sig figs. And so a lot of people will say 1 inch is 1 inch. Right? These two numbers are exactly the same, but they aren't exactly the same. Those two numbers are quite a bit different. And the difference arises in the degree, how precise they are. This 1.0 inches is much more precise than 1 inch. Because at 1.0 inch, what we do is we take half the smallest digit. The smallest digit would be 0.1 inches. Take half of that, and so what we get is this one would be anywhere from 1.04 on the high side to 0.96 on the low side. So anywhere from 0.96 inches to 1.04 inches. Now you compare that to this, and you see how much more precise. this number is, because 1.0 could only range from 0.96 to 1.04. Those would round to 1.0. Does that make sense? Okay. All right, so let's say you're going in for surgery. You know, if you're going in for surgery, you want higher precision. You want the surgeon to be very precise. You know, you want to cut right there. You don't want to be half an inch off, you know, or an inch off. You want high precision. And the high precision is given by the number of sig figs that we have. And so let's go to this. So what we're looking for is we want the dimensions to cancel. So the hours cancel and takes us to minutes. But, you know, sometimes we go the wrong direction. So is going from hours to minutes getting us closer to weeks or getting us further from weeks? Further. We're getting colder rather than warmer here. And so since this is getting colder, what I do is, maybe that's not the best. Is there some other direction I should go here in getting rid of hours? Yeah. Or maybe I should go this. 1 day is equivalent to 24 hours, right? And so is that getting, that seems to be getting warmer rather than colder here. And so, but I'm not there yet. But no big deal, because in dimensional analysis, we just add another conversion factor. We just keep adding and adding more conversion factors until we get there, or we're lost. You know, maybe we get lost or we get stuck. If we get lost or stuck, all we do is we back up and then start over again. You know, and so eventually, most people will get the correct answer because it's just a step by step. This is a little thing. You know, it's not like in problem solving. It's not like you have the whole route figured out. You know, you just take it a step at a time. So if you're doing, let's say, I'm not a marathon runner, but if you're doing a marathon through some unfamiliar city, you do it step by step and just follow the path as it goes along. You don't think about the entire path at once, right? And figure out, well, maybe you do, maybe you don't. What I do here is I just do it one step at a time and then see, you know, like I screwed up here, but in this case, days. I need to get rid of days, so what can I relate days to? Weeks. So I can say 7 days in 1 week. All right, so the days cancel, and that gives me weeks. Well, that's what I want. I want weeks here. And so the dimensions have worked out. Now I just got to work out the numbers. So it's going to be 672 divided by 24 divided by 7. So I would do that in a calculator. Let's see, do I have my calculator still up here? Maybe I got rid of it. So I do 672 divided by 24 divided by 7. 4 weeks. Now, this is a tricky thing here, and that is 672 exact or approximate? You know, and it depends on. It's ambiguous. We don't know. Is that exact? Is it exactly 672 or approximately 672? And so since that's a little bit ambiguous, I'm going to call this exact. And so we'll just define as exact. The reason I'm going to define it as exact is because I don't want to say this. I don't want to say in approximately 672 hours, there's approximately this. I'd rather say in exactly 672 hours, there's approximately 4 weeks. Now, this is a little bit tricky here, and this is probably not the best problem, but if this is exact, that's infinite sig figs. Is this exact or approximate? 1 day, 24 hours. That's exact. Is this exact or approximate? This is exact. And so it turns out if this is exact, exactly 672 hours, then this is going to be exact. And so there's exactly 4 weeks in 672 hours. Now, if this were approximate, then I'd have to change this to reflect that, you know, because it's less precise, it's a little bit uncertain. And so if this is approximate, then I'd have this. And so if I define this as exact, now if I define this as approximate, then I'd say in approximately 672 hours, how many weeks are there? Well, that's 672, they just picked this number. It could have been 673. If it's 673, would that be exactly 4 weeks? No, it'd be 4 weeks and 1 hour, right? But if this were approximate, then this is what we think. If this were approximate, it would range from 671.5 up to 672.4, just like the sterling silver, had that little range, right? And so this would be the little range in this. Well, then we have to reflect that, because since there's some wiggle room here in this, there's going to be wiggle room here in the weeks. And so what we say is that this is 3 sig figs, therefore the weeks are going to be looking different. And so if that's approximate, our answer would look different. It would be 4.00 weeks, which means that this could range from 3.95 up to 4.04 weeks. Because of the wiggle room here, there's going to be wiggle room in our answer. Does that make sense for that? And so this is something that we're going to have to keep track of, which makes this more difficult than just standard algebra. Because standard algebra, we wouldn't keep track of these things at all. What's exact, what's not exact. Now, when we look at their answer, they haven't started keeping track of it. And the reason I'm starting to keep track of it is because I don't want to go back and correct these things later for this. So anyway, they convert hours to days, and then days to weeks, and then calculate the number. The formatting's off a little bit here. So that makes sense. About 4 weeks. What distance expressed in miles would an automobile travel in 3 hours at an average speed of 62 miles an hour? So 3 hours, is that exact or approximate? Well, it's a little bit ambiguous, but probably the easiest thing to do is to say it's exact. In exactly 3 hours, approximately how many miles will we travel? Because of this. Is 62 miles an hour exact or approximate? That's approximate. And so what we don't want to do is we don't want to do this. In approximately 1 hour, approximately how many miles will I travel? That's putting uncertainty in the hours and putting uncertainty in the miles. What we want to do, the best thing to do, is to keep one exact and then put all the uncertainty in the other. And so in exactly 1 hour, approximately how many miles will we travel? And so what that means is something like this. And so 3 hours, this is a little bit ambiguous, because if this were exact, then it has infinite sig figs. If it's approximate, then it only has 1 sig fig. And so if this is approximate, then it could range anywhere from 2.5 to 3.4 hours. Well, in 2.5 to 3.4 hours, that's going to be a big range in miles, right? And so the range in miles is going to be imprecise. You have a huge range. Whereas if that were exactly 3 hours, then we can narrow down the range of miles much more precisely. And so what we'll do is we'll just assume it's exact. 3 hours. If we assume that that's exactly 3 hours, and then we want to figure out how many miles, then we got to get rid of hours. What can we do? We can go from hours to minutes, right? Or we can go from hours to seconds. Or in this case, when we're given a problem like this, they're giving us a conversion factor here, 62 miles per hour. And so if they're giving us a conversion factor there, then we usually write it down. 62 miles is equivalent to 1 hour. Now, is this exact or approximate? Approximate. So should we say we drive approximately 62 miles in approximately 1 hour? Or should we say in exactly 1 hour we drive approximately 62 miles? In exactly 1 hour we drive approximately 62 miles. We just try to keep it in 1. And so in exactly 1 hour, this is not 0.5 to 1.4 hours, this is exactly 1 hour, we're going to drive approximately 62 miles. Now the 62 miles can range from anywhere from like 61.5 up to 62.4, right? There's going to be some uncertainty associated with that. But if we're putting uncertainty in both these terms, it's going to get all mixed up. And so that's it here. $186 miles. 186 miles. Now, according to the sig fig rules, this is the way we deal with it. If this is exact, this has infinite sig figs. How many sig figs does this have? This has 2 sig figs. And so if that has 2 sig figs, then it turns out that we're only allowed 2 sig figs in our answer to keep the uncertainty about the same level. Although we'll see it's not entirely correct, as somebody noted this morning that uncertainty seems off. But the uncertainty here is going to, well, how do we write this in 2 sig figs? In terms of 2 sig figs, 186 miles is going to be 190 miles, or 1.8 sub 6 times 10 squared. The sub 6 is not significant. That's going to be a drop digit, so this is only really 2 sig figs. And so if I drop 6, I have to round it up. So this comes out to 1.9 times 10 squared miles here, or 190 miles. Now the 0 may or may not be significant here. In this case it isn't, may or may not, but it's ambiguous, be significant. Okay with this? All right, so this makes sense. The significant rule stuff actually isn't the way. Significant rules is a simplified version of how scientists handle uncertainty. How scientists handle uncertainty is via, let's see, where was that? How scientists handle uncertainty is by using propagation of errors. They say propagation of uncertainty here. A lot of people just call it propagation of error. This will give you a better idea of the uncertainty in your answer here. But the only problem with this is it requires calculus. This is the calculus stuff here. And so the math is a little bit more, although the calculus is not difficult, the math is a little bit more than the scope of this class. And so what we do is we take these rules here, actually this would be, the law of propagation of uncertainty, and make these rules here. These rules are going to have a lot more exceptions. These rules aren't perfect. These are called the rules for significant figures. And they aren't perfect, and sometimes they overestimate and sometimes they underestimate the magnitude of uncertainty. But the math is a heck of a lot easier, and so that's why I do it. This number is a little bit tricky too. So piggy bank contains 2,608 pennies. Is that exact or is that approximate? This would be more exact as long as they didn't miscount it. If it's just an estimate, then you wouldn't be this precise. But can you have a fraction or half a penny? No. And so this has got to be exact. And so we got to figure out how many dollars. You probably can do this in your head. don't really need to do it, but if we set it up dimensionally, then we get rid of pennies, convert it to dollars. 100 pennies per dollar, $26.08. How about this? Is this exact or approximate? Exact. And so in this case, it's exact. But in other cases, it's a little bit more ambiguous. So we just follow a set of rules. Yeah. All right, we'll do more calculations in a little bit, but we'll look at the metric system next. The metric system, we have SI. These are SI, the International System of Units, which is based on the metric system. So the SI unit, do you know what the SI unit for mass is? The kilogram. The SI unit for volume? The cubic meter. But chemists don't always use that. Kilograms too much for our laboratory. So typically we use grams for mass. You know, that's different than pounds and ounces. Pounds and ounces is actually weight. You know, pounds and ounces will change on Earth versus the moon, but grams and kilograms won't. You know, number of grams and number of kilograms is always going to be the same. But we use grams, and for volume, we don't use cubic meters. We use milliliters or meters. Then we have metric prefixes. Some metric prefixes that will start off with kilo is 1,000, milli is 1/1,000, kilo, milli. We'll see some units here. Let me just fast forward here. And so some units that you should know, kilo for sure, milli for sure, you should know those. Centi, well everybody knows, 100 centimeters per meter. So centis, 1/100. Tera, you know, if you go to buy a hard drive, you can get terabytes, 1 terabyte, 2 terabytes of data. That is a trillion. Used to be gigabyte drives. Gigabyte drives are a billion bits. Mega is a million. Kilo is 1,000. Hecto, I wouldn't bother. Deca, I wouldn't bother with that. Hecto, deca. Deci, biologists use deci. We don't use it that much. Deciliters. Centi, yes. Milli, yes. Micro, yes. Micro is 1/1 million. Nano is 1/1 billion. And pico is 1 trillion. So pico is important. Where did you see pico before? The size of an atom, right? Picometers. And so those are some of the metric prefixes. So again, hecto, deca, deci, don't know, but you should know the others. Okay, this is the difference between mass and weight. We're going to use these interchangeably, but they are different. How do you measure weight or mass? We use balances. I don't know what that is. That doesn't look like a balance. Then we have our units. So the standard unit of mass is the kilogram. This is the SI unit, a kilogram. And so how is a kilogram defined? You know how a kilogram is defined? Like for example, how would you know if you had exactly 1 kilogram? What is exactly 1 kilogram? 1,000. Well, then how would you know what a gram is? Exactly. There are exactly 1,000 grams in a kilogram, but what is a kilogram or what is a gram? How are they defined? That is, you know, I always wondered this. Did some scientists pick up a stone or a rock, you know, and said, okay, this is about a kilogram, so this is going to be defined as a kilogram. And so that became the standard. Well, a meter is easier to define. A meter is the length of the path traveled by light in a vacuum in 299,792,458 seconds. And so we know that, that's the length light travels in that short of time. That's extremely short time. That's a meter. But how is a kilogram defined? That I don't really know, but I do know, if you wanted to know what exactly 1 kilogram is, there is exactly 1 kilogram. Where can you find exactly 1 kilogram? You could find exactly 1 kilogram locked in some vault in France. This is the definition of a kilogram here. It's this piece of metal here. This piece of metal is exactly 1 kilogram. This metal is made out of platinum and iridium, And so if you were curious, if you had a kilogram, you'd have to compare your mass to this mass, because this is the definition of the kilogram. Which makes things kind of inconvenient, right? Because this is France. You can't make your own. Probably can make your own. It's very close to it. But anyway, a kilogram weighs 2.2 pounds. So is that exact or approximate? Is there exactly 2.2 pounds in 1 kilogram? No, it's approximate. It's 2.202 ... It keeps going on. It's like pi. Is pi exactly 3.14? No, it's approximate. So same thing here. So it's okay. So there's some mass. Well, length, we have some kind of standard for length, which is good. Cubic centimeter or milliliter. Cubic centimeter and milliliter are the same thing. A liter is 1,000 milliliters. A centimeter, there's 100 centimeters in a meter. Now this is a little bit tricky. 1 inch has 2.54 centimeters. Now let me ask you this. Are there exactly 2.54 centimeters in an inch or approximately 2.54 centimeters in an inch? You would think approximate. I would think approximate too, but you know what? This word here tells me it's exact. Because somebody defined, it's like the kilogram. Somebody defined the kilogram. This is 1 kilogram, so therefore that is exactly 1 kilogram. Well, somebody defined this. 1 inch is defined as 2.54 centimeters, so that they have some relationship between the inch scale and the centimeter scale, and this is how it was defined. So this is exact. There's no uncertainty here. It's exactly 2.54 centimeters in an inch. There's a micron. That's a cubic centimeter. This is a cubic, what is that? Cubic meter. 1,000 cubic centimeters in 1 liter. In other words, 1 liter has 1,000 milliliters. We'll look more at these. Here's the metric relationships. Actually, we're out of time. So we'll stop here and then we'll continue.